Yep,
Yeah.
I'm ready.
All right.
All right. Hello, everyone. My name is Hessam Mirsadeghi, and I will be talking about UCX on AWS, explaining a recent effort for adding support for Amazon EFA in UCX. And here's a short outline of my talk. I will first talk a little bit about HPC in the cloud, and then move on to explaining how the Elastic Fabric Adapter, or EFA, from Amazon helps HPC in the cloud. And then I will explain what we did for adding EFA support in UCX. And we will also see some related performance results. HPC in the cloud is an emerging trend that provides an alternative to traditional supercomputers for getting access to HPC resources. And it has some interesting advantages compared to traditional supercomputers, such as easier and quicker access to HPC resources. You don't have to go through the process of getting access to a supercomputer that is usually not a straightforward process, and it's not easy, and certainly not possible for everyone. And with HPC in the cloud, you don't have to worry about any maintenance costs, anything related to maintaining a supercomputer, which can be quite challenging. And another advantage is that the elastic nature of cloud resources, as well as the pay-as-you-go cost model, enables the users, provides actually the users with more flexibility to provision and deprovision resources as the demands of the corresponding workloads change. And a main question here for HPC in the cloud is, what about performance, and in particular the networking performance when it comes to HPC in the cloud? Because after all, a main feature of traditional supercomputers is that they have this very highly optimized interconnection network for communication between the nodes. And in particular for Amazon, Amazon's efforts to support HPC-grade communication performance on AWS is centered around the Elastic Fabric Adapter, or EFA. EFA is this HPC-optimized network interface introduced by Amazon for EC2 instances. It provides 100 gigabit per second link bandwidth. It has OS bypass and RDMA capabilities, similar to InfiniBand, for instance. And it also supports GPU direct RDMA on certain instance types to enable direct communication between GPUs on the cloud. And here we see the software stack on AWS with and without EFA. In both cases, we have the application and some communication libraries such as MPI at the top. And then on the left side, without EFA, all communications go through the traditional TCP/IP stack, and which is in the kernel space. But as shown on the right side, with EFA, we will get direct access to the NIC from the user space. And this usually happens through another middleware communication library, such as libfabric, or as a result of this work, also UCX. Currently, EFA supports and provides two transport protocols that kind of represent two different communication modes that you can use with EFA: unreliable datagram, or UD, and the scalable reliable datagram, or SRD. UD is very similar to UD from InfiniBand. It is connectionless, unreliable, without any ordering guarantees. It supports send-receive semantics with a 4 kilobyte MTU. It doesn't have any RDMA read, similar to InfiniBand, doesn't have any RDMA write, well, similar to UD on InfiniBand, of course. And it is also subject to the same flow limits as TCP and UDP on AWS network, which means that the bandwidth is capped for each single UD flow to 10 gigabit per second if the two nodes are in the same cluster placement group, and it will be lower than that if they are not. But the more interesting and more important transport for EFA is the scalable reliable datagram, or SRD, which has been specifically designed by Amazon for EFA. Similar to UD, it's a connectionless protocol, but unlike UD, it is reliable. The hardware provides the reliability, so the high-level communication protocols don't have to worry about packet drops, retransmissions, and things like that. But it doesn't provide any ordering guarantees, and that means that the packets can and will most certainly arrive out of order at the receiving side. And it also, similar to UD, it has support for send-receive semantics, but with an 8 kilobyte MTU. And in addition to that, and this is the main difference here, is that it supports RDMA read as well. And it doesn't have any RDMA write, and it is not subject to any flow limits. So it can potentially achieve the full EFA link bandwidth on AWS. Let me briefly explain why Amazon chose SRD, and that goes back to certain characteristics and requirements of AWS data center and its users. AWS engineers wanted to avoid creating islands of specialized networks. And that is because having the instance choice and having the capacity right away is very important to AWS and its users. And this can be achieved only if you have a large capacity pool, and creating these islands of specialized networks such as InfiniBand kind of works against that. And another reason is because AWS uses commodity Ethernet switches in its network, along with the ECMP routing. And with the ECMP routing, you have this static hash-based mapping of flows to different paths in the network to achieve load balancing. And this mapping is static in the sense that it is fixed for every given flow. For each single flow, it is fixed to preserve the per flow ordering semantics of TCP. And this means that hash collisions can create hotspots, which can result to packet drop, retransmissions, all of which increases latency and decreases throughput, which you certainly don't want for HPC communications. And this is where the relaxed ordering semantics of SRD come to the rescue. And SRD avoids ECMP limitations by extending multipath routing even to the packets that belong to the same flow. And this is done by the SRD sender controlling ECMP path selection by manipulating the packet headers that it in. And this way, the SRD sender proactively sprays each single flow over multiple paths in the first place. And this allows to minimize the chance of creating hotspots in the first place. And also, this is done in a way to avoid existing hotspots and suboptimal path in the network. It also resolves head-of-line blocking issues and allows for a faster recovery from link failures, for instance, because the packets don't have to wait for a connection to be reestablished. They can just use another alternative path that exists in the network. And AWS network has a lot of these alternative paths. These are 4 of the main instance types that currently support EFA. There are more, but I'm just showing like 4 main. And as you can see, 3 of them have NVIDIA GPUs as well. And the highest end one is the P4D instance type, which has 4 EFA NICs and 8 A100 GPUs with NVSwitch. And it also supports GPU Direct RDMA. And of course, it is like the most expensive of them all. And what is the main motivation for adding EFA support in UCX? Well, we want to be able to deliver better than TCP performance on AWS, because without EFA support, the UCX usage on AWS will be limited to TCP. And here in this chart on the right side, I'm showing the OSU MPI bandwidths between 2 P4D instances when we use OpenMPI plus UCX over TCP for both host-to-host and device-to-device communications. And as we can see, we can only achieve about 1.2 gigabyte per second bandwidths, which is almost 1/10 of the actual EFA link bandwidths, which is about 12 gigabyte per second. So in order to achieve the full potential of EFA, we really need to support EFA and its corresponding transports in UCX. Another important reason is because this will enable UCX software ecosystem on AWS, and this will enable different libraries such as Spark and UCX-Pi and Dask from Rapids, because these libraries and frameworks, these use UCX as their communication backend. And in fact, a lot of effort has been put into making UCX a better match for these kind of libraries. For instance, having more isolated error handling and a better integration with Python progress model by, for instance, having the wake up feature that we have in UCX. So we really don't want to replicate all this effort on top of libfabric, for instance, and it would be great if we can reuse UCX. To have EFA support in UCX, we have made it, some changes at the UCT layer to add support for each of the transport protocols that EFA provides, namely UD and SRD. And we started with UD because UCX already has support for UD from InfiniBand for UD verbs. And EFA UD is also exposed through the verbs API. So we thought it should just work out of the box and should be straightforward, but it didn't, because EFA is not 100% IBTA compliant. It is not InfiniBand. So for instance, some of the differences with EFA, you don't have any guarantees on the completion order of work requests. And this means we cannot use like a batch completion processing logic that we already use in UCX for UD, for instance. And EFA only supports a subset of memory registration access flags, unlike InfiniBand devices. It only supports local write, of course, in addition to local read, which you always have. And on P40 instances, it also has remote read. And it also doesn't have support for interrupt-based completion notifications. Taking all these different limitations and differences into account, we made the following changes to make UD verbs work over EFA as well. First of all, we added a new EFA memory domain to be able to capture like EFA specific features and limitations. And this will allow us to open an EFA memory domain at the UCT layer and check whether we have any EFA device on a system or not. And if we do, what are its corresponding attributes. And then we have also made updates to the UCT IB device itself and added some extra fields to know what are the exact registration access flags that the corresponding device supports, and whether the device has completion queue notification mechanism, and also does it guarantee any in-order work request completion or not. Having all this information, then we use it in the UD verbs itself. We update UD verbs accordingly. For instance, one of the changes is we say don't use IBV send solicited flag if you don't have the completion notification supported. Otherwise, the send operation will actually fail. And avoid using batch completion processing if there is no in-order work request completion guarantee. For instance, rather than using a queue, use a hash table. Having made all these changes, here are the performance results that we got with UCX plus UD over EFA. And I'm using OSU MPI latency across different message sizes. And I'm comparing the results with TCP for both host-to-host and device-to-device communications. And I'm also comparing the results with RDMA core. So on the leftmost chart here, this dark blue line shows host-to-host latency with UCX plus UD. As we can see, and the light blue line shows the results for RDMA core. We can see that we are very close to RDMA core for small messages for host-to-host latency. And host-to-host latency is 44% lower than what we got with TCP and UCX. And for device-to-device communications, this green line shows UCX-UD for device-to-device communication. And the latency for small messages has been 47% lower than TCP for device-to-device communications. And we see that the device-to-device communication latency is higher than host-to-host, which is because of the overhead that we have due to extra host-to-device copy that we will have with UD, as well as TCP, of course. Another observation is that on this rightmost chart here for large messages, we can see that the latency with UD for device-to-device communication is actually very high. And in fact, it is even higher than TCP. And the reason is because, first of all, we don't have GPU direct RDMA with UD, which is same for TCP. And that means that we used a copy-based pipeline protocol, but the problem is for UD, the copy chunk size of this protocol will be smaller. It will be around 4 kilobytes because of the MTU size that we have with UD. And for TCP, this copy chunk size is actually larger. So that's why we see that TCP actually gives better latency for large message device-to-device communications. Here I'm showing the OSU MPI bandwidth results, again for UCX-UD and UCX TCP, device-to-device and host-to-host. And as we can see, the maximum bandwidth that we have been able to achieve with either TCP or UD is just around 1 gigabyte per second. And this is mainly because of that flow limit that we have for both TCP and UD on AWS network. And we also see by this green line here, that the bandwidth for device-to-device communications with UD is very low, which is for the same reasons that I explained on the previous slide. Moving on to SRD support, which is the more important protocol actually. For adding SRD support in UCX, we added a new UCT transport at the UCT layer, which will implement the UCT interface over SRD and EFA. And two main classes of functions should have been implemented, the UCT active message API and UCT RMA API. And the active message API mainly would involve AM short, AMB copy, and AMZ copy functions. And for RMA and with SRD, we will have get short, get B copy, and get Z copy. And SRD's relaxed ordering semantics create some challenges when it comes to implementing the UCT AM interface. And first of all, note that packets must be delivered from UCT to UCP in order. And that is required to preserve the correctness for tag matching semantics, for instance. Because two messages, for instance, that are two tag messages that are sent with the same tag, they have to be received in order at the receiver side. And UCP relies on the UCT to deliver these messages in order to UCP. And to achieve that with SRD, we added a sequence number to each outgoing SRD packet. And at the receiver side, we buffer all the out-of-order packets. And we deliver these out-of-order packets to UCP. And in fact, we deliver each packet to UCP only if we know that all its preceding packets have already arrived and we have already delivered them to UCP. That will guarantee that ordering requirement that UCP expects from UCT. And on top of that, we also use a window-based flow control to avoid a fast sender overwhelming a slow receiver, and also to be able to limit the amount of buffer space that is required for out-of-order packets. A good thing is that we didn't have to do anything about fragmentation and reassembly of large messages with SRD in particular, because UCP already handles that for all transports. And each UCT interface only advertises the maximum message size it can deliver without fragmentation and reassembly. Another challenge with relaxed ordering semantics goes back to how we process request completions, as well as the flush operations, the flush operation at UCT layer. The flush operation is used to notify the user when all the communications all the communication requests that have been posted so far are completed. And with guarantee for in-order request completion, which is the case with InfiniBand, what we do is that we enqueue each outstanding request, as well as any flush operations that might have been issued, into an outstanding queue. And whenever a request such as R of K, for instance, in this example completes, we start dequeuing all the elements from the head of the queue up to and including R of K. And we call the corresponding callbacks if there are any. And we do this because completion of R of K, when you have in-order guarantees, means that all the requests before it have necessarily been completed. But without guarantee for in-order completion, we cannot do that. So what we do is that whenever a request such as R of K completes, we only remove that request from the queue. But in addition to that, to support flush, what we do is that every time we remove a request from the queue, we check to see if we happen to have any flush operation at the head of the queue. If that is the case, we dequeue that flush operation and call its corresponding callback. For instance, in this example, if instead of R of K, we had R of I being completed, we would have removed R of I and also the flush operation that now happens to be at the head of the queue. And we do that because if you have the flush operation at the head of the queue, it implies that you don't have any outstanding requests before it. So that ordering requirement has been met. For the RMA interface with SRD, we implement the get operations, the get class of operations, using RDMA read over SRD. We don't implement any put operations because there is no RDMA write with SRD. And a good thing about RDMA read is that EFA device itself takes care of fragmentation, assembly, and all ordering semantics for messages up to 1 gigabyte. But still, 2 RDMA read operations can complete out of order. And that impacts the fence operation at UCT layer. And that means that the fence operation cannot be a no-op anymore, which is the case for InfiniBand. In InfiniBand, you have guarantee for in-order completions. So the fence operation happens to be a no-op. But this cannot be the case anymore with SRD. And to address that, this is a design that we have. And basically what we do is that we use an additional queue. We call it an RMA queue, showing it here in the center, to keep track of all get operations, all outstanding get and fence operations, and their relative order. So what we do is that every time a get operation is issued, we first check to see if we have any active fence operations in the RMA queue or not. If you don't have any active fence operations, we just post the get operation to the device. If there are any active fence operations, we don't post, because otherwise we don't have any control over the order in which it will be completed. Instead, we add that get operation to the RMA queue. On the other hand, every time a fence operation is issued, we check to see if we have any outstanding get operations in the RMA queue or not. If you don't have any outstanding get operations, fence up becomes no up, because there's nothing that we want to worry about its ordering. But if we do have some outstanding get operation in the RMA queue, we will add an entry for the fence operation to the RMA queue. On the other side, every time a get operation completes, we go ahead and remove its corresponding entry from the RMA queue. And then again, we use a similar logic that we had for flush. We check to see if after removal of that entry, we happen to have any fence operation at the head of the queue. And if so, we remove any of such fence operations from the head of the queue, because again, being at the head of the queue means that you don't have any outstanding get operations before you. So it's okay to clear that fence operation and go ahead and post every get operations that happen to be after that fence operation in the queue. Here are some performance results with UCX plus SRD. I'm showing OSU MPI latency results, again, across different message sizes for host-to-host, device-to-device communications, again, comparing with RDMA core. And this time, I am also showing the results with OpenMPI plus libfabric with the EFA provider from Amazon. On the leftmost chart here, I'm showing results with the small messages. Again, the dark blue line, the latency for host-to-host communications with SRD. Again, we see that we are kind of close to RDMA core. And another observation here is that before 32-byte message size, we're seeing a lower latency with UCX compared to libfabric. But this is because when I got these results, libfabric provider did not use inline send for small messages. And apparently that has been updated now. So if you get these results again, we should see a lower latency for libfabric. On the other end of the spectrum for large messages, a good observation here is that we see the same latency for device-to-device communications with UCX plus SRD as host-to-host communications. And this shows that we've been able to successfully use GPU direct RDMA with UCX over SRD. And another important thing that I have to note is that we see a higher latency with libfabric for large messages. But this is mainly because when I got these results, I did not have this PHY EFA use device RDMA environment variable set, which is not set by default. And having it not set disables RDMA read for libfabric. So the results that you see with libfabric here are basically from a copy-based protocol. It is not using RDMA read. So once that is enabled, we should see lower latency with libfabric. But I did not have access to the nodes anymore. So unfortunately, I could not update the results for libfabric. And here are the bandwidth result with UCX plus SRD. A good observation here is that we see for both host-to-host and device-to-device communications, for both host-to-host and device-to-device communications, we have been able to saturate the EFA link bandwidths and achieve 12 gigabyte per second bandwidths. And getting back to the main motivation that we had in the first place, we can see we have been able to achieve, compared to TCP, 10 times higher bandwidths with UCX when we use when we have the support for SRD. For conclusions, EFA plus SRD provides AWS users with HPC grade communication performance, but SRD is a protocol that has relaxed ordering semantics. And that is something that is necessary to achieve high bandwidths on AWS network. And to support EFA in UCX, we have added a new SRD transport in UCX that will allow us to deliver the main benefits of EFA to UCX users on the cloud. The code status currently is still a work in progress, actually, and requires thorough reviewing and testing, I would say. And here are the 3 pull requests that I have for EFA support in UCX. One of them is for the EFA memory domain itself that will be shared for both, that will be used for both UD and SRD. And another one addresses the changes that is required to make UD work over EFA and a separate one for SRD. Thank you very much. That was all from me. I will be happy to answer any questions you might have.
So Dimitri posted a question in chat. It looks like it's about the flushes.
Mm-hmm.
He asks, what if you have the following case? RI, RJ, F, RK, and RJ is completed before RI. If I got the proposed implementation correctly, you will complete F flush operation, but it has to be completed after.
No, I don't complete flush, because if RJ completes, I remove RJ, and then I don't have any flush operation at the head of the queue. At the head of the queue, I have R of I. So the flush operation is dequeued only if it happens to be at the head of the queue.
Oh, I see. I see. Thank you, Hassan. Yeah.
Yeah.
Let's explain.
Yeah. But a shortcoming of this design, because it's like the one way to do it. One shortcoming is that I'm still using a queue because I want to be able to capture the relative orders, right? And that means every time a request is completed, I have to scan the queue to find the request. Of course, this can be addressed like using a hash table as well, but that's not something I have done yet. We just wanted to have like a simple implementation first to see some early results.
Yeah, I see. Thank you.
Okay, Sam, also wanted to comment that maybe we will consider moving some of flash logic to UCP, especially in order to coordinate between different rails. Because, for example, if you use a RMA with multiple rails, it's not enough to flash only one. We have to kind of flash all of them together. So maybe we can consider more relaxed requirements for a transport level flash. Maybe especially removing the iFace flash and keeping only endpoint level flash. And then most of the logic would actually be in UCP.
Would be in UCP.
Yeah.
Okay.
Because if it doesn't make a lot of sense to have iFace level flash in UCT, because if we still need this counter on UCP level, because we have all these pending operations, and it's not enough to keep order between the UCT operations themselves, because if some operation is done in UCP as part of a pending callback, it's actually considered earlier than other operations that come directly from API calls. And this is something that UCT can't really track.
But so you're saying that in that case we don't even need UCT level flash?
So I think that maybe we should consider a different design of the flash and have less requirements on UCT. In particular, the iFace flash could be moved to UCP and maybe other things as well.
But how will we handle this in this case if we remove iFace flash from UCT?
You mean that it would not be efficient to flash?
Yes, we will have to go through all the EPs while it would be enough to go through just DCIs.
That's right. And what about defense operation? Would it help if we move a defense operation to UCP layer, Hassam?
I'm not sure what that would exactly mean, because even if we have it at UCP layer, for the sake of UCT itself, we still need fence, right? Because at the very least, I might be using just UCT.
Yeah, if you could have only fence per endpoint and not for iFace.
Not for iFace.
If you're using UCT, you have to fence all the relevant endpoints. and track whatever you're using.
Yeah, specifically for iFace, you're saying we might not need a fence separation, but for UCT-EP, we still need that,
Yeah,
right?
yeah, we need some basic building block.
Yeah.
Will it help EFA in some way?
I mean, it doesn't make much difference because I still need it for EP, right? And for iFace, because I have this design per EP, right? Also for iFace, yeah. It will if we have it for iFace as well, then we will have to kind of replicate that logic for iFace as well. So if we don't need it at iFace level, then I will only need to use it at EP level.
But you would still need something.
I will still need something, yeah.
Okay, so it's the top of the hour.
I have one last question for Sam. In the results that you presented, you compared AWS ONP/Leaf Fabrics to UCX or OpenMPI plus UCX. It wasn't
Oh no,
clear.
this is all OpenMPI plus UCX. So it's all MPI results.
Okay.
Yes.
Not perfect. So in actual, pretty much you get the same results when compared, let's say, to tuned Leaf Fabrics revision, right?
Right.
Okay. And what is your, in terms of like upstreaming and getting this into main tree, what are the plans?
Well, I think I have to find some more cycles to work on it again. There are some issues that I have to resolve. For instance, for the memory domain pull request to pass all the tests. And then the plan is to have that one merged first, because it will be like used for both UD and SRD. And then for UD, I'm not 100% sure if we want to have UD upstream or not, because the main benefits come with SRD. So then after that, we could do two things. We could either just jump to SRD and at least prioritize it in terms of upstreaming it over UD. And for SRD, again, we really need a lot of reviews and a lot of testing, and hopefully also testing from Amazon.
Well, we can discuss, we can work on in terms of like CI allocation and allocating some funds for getting AWS machine for CI. This can be done.
Yeah, that would actually be great.
Yeah.
And I'm thinking maybe we can get some reviews from Amazon as well.
We can try. We can promise this. And yeah, but the allocation of machine for sure, it's relatively straightforward.
Okay, and I was thinking maybe they already have some tests for, I mean, they certainly already have some tests for EFA, and whether we could just like reuse them on their CI or something like that.
Well, I think the way our CI works, we have all like UCX-UD tests. There's like thousands of tests there. So this pretty much would beat hell out of any transport out there. So if you pass this, I think you will be in very good shape.
Yeah.
And in terms of MPI testing, we typically leave it up to MPI community. So MPG guys and OpenMPI guys, it will be up to them to verify that works.
Right.
Okay, cool.